Now we are going to another important concept, that is Lipschitz condition. Lipschitz condition. Lipschitz function. First we define what is a Lipschitz function. A function which satisfies Lipschitz condition is known as a Lipschitz function. So what is Lipschitz condition? So for let A is a part of A is a part of a function f from A to R is said to be satisfies Lipschitz condition if for all x comma y for an A, modulus of f of x minus f of y less than or equals k into modulus of x minus y, where k is a constant. This k is known as Lipschitz constant. K is a constant which is known as Lipschitz constant. So this is the Lipschitz condition. A function which satisfies this Lipschitz condition is known as a Lipschitz function. So f is A is a part of R, and a function f from A to R is said to be satisfies Lipschitz condition if for all x comma y for an A, then modulus of f of x minus f of y less than or equals k into modulus of x minus y, where k should be positive. That is again another crucial point. K need not be negative and never become 0. So for all there exists a k greater than 0 such that modulus of f of x minus f of y less than or equals k into modulus of x minus y. This k is known as k is a positive constant which is known as Lipschitz constant. So actually consider y equals f of x. Consider a line or consider this, that is y equals f of x. Consider a curve. Consider this curve y equals f of x. This function. So suppose here it is x, then y equal, and this is f of x. X and f of x. So then you can consider a straight line which join the points ordered pair x f of x and ordered pair y f of y. Okay, or ordered pair x f of x and u f of u, whatever we know. So actually this is the y equals f of x. So and x and y. Here it is, suppose it is y, means, or it is u. If it is f of x minus f of u less than or equals k into modulus of x minus u. So this is the point x, corresponding point. X ordered pair x f of x and this ordered pair y f of y. Okay. So what about mod f of y minus f of x? F of y minus f of x by y minus x. F of y minus f of x by y minus x is nothing but the slope of this line or slope of the line segment joining the points, suppose it is P and Q, joining the points P and Q. So the geometrical interpretation of this Lipschitz condition is nothing but the slope of a line joining these 2 points ordered pair x f of x and ordered pair y f of y on the graph y equals f of x being bounded by some constant k. This is rewrite as modulus of f of x minus f of y all divided by modulus of x minus y less than or equals k, where k is positive. So the geometrical interpretation of Lipschitz condition is nothing but, or Lipschitz function is nothing but, it is nothing but the slope of the line segment joining the 2 of the points ordered pair x f of x and y f of y on the curve y equals f of x, which is bounded by some constant, positive constant k. That is the geometrical interpretation of Lipschitz condition. Okay. Now, now we are going to an important result. If f is a Lipschitz function, then f is uniformly continuous. F is a Lipschitz function, then f is uniformly continuous. Means, if f satisfies a Lipschitz condition on a given domain A, then f is uniformly continuous on A. So this is another criterion for the uniform continuity of a function. So in order to prove a function is uniformly continuous, it is enough to show that a function f is Lipschitz function, means it satisfies Lipschitz condition. That is, that A is a part of R. And if you define a function f from A to R, such that f satisfies Lipschitz condition or f is a Lipschitz function, then f is uniformly continuous. That is our requirement. How to prove this one? Its proof is, assume f satisfies Lipschitz condition. F satisfies Lipschitz condition. That is, for all x comma y fall in A, there exists a constant k greater than 0, such that modulus of f of x minus f of y less than or equals k into modulus of x minus y. Okay. Put on delta equals epsilon by k. Since k is positive, epsilon is the smallest positive quantity. Delta is again smaller than epsilon. So put delta equals epsilon by k. If x minus y less than delta, if x minus y less than delta, then here, then from this equation 1, so 1 implies modulus of f of x minus f of y, which is less than or equals k into, which is strictly less than k into delta, y, provided mod x minus y is strictly less than delta. If mod x minus y less than delta, equation 1 reduces to mod f of x minus f of y less than k into delta equals k into, what is delta? Epsilon by k equals epsilon. That is, if modulus of, this can be concluded as, if modulus of x minus y less than delta, then modulus of f of x minus f of y strictly less than epsilon. This is nothing but the definition of uniform continuity of a function. Okay, that is, if mod x minus y less than delta, then modulus of f of x minus f of y less than epsilon. So this proved that when a function satisfies Lipschitz condition, then that function is strictly uniformly continuous on the. Agree. But what about the reverse inclusion? What the reverse of this statement? If a function is uniformly continuous, then is it satisfies Lipschitz condition? If f is Lipschitz implies f is uniformly continuous. That is we proved. What about the reverse inclusion? Is it true? So we check it. Consider, let's define a function g from I to r. G from I to r, where I equals closed interval 0 to. I equals closed interval 0 to, closed and bounded, and is defined by g of x equals root x. G of x equals root x. First we check whether this function is uniformly continuous on I. What about modulus of g of x minus g of y? Modulus of g of x minus g of y equals modulus of root x minus root y. Okay. modulus of root x minus root y can be rewritten as, this is nothing but modulus of root x minus root y into modulus of root x plus root y all divided by modulus of root x plus root y. Multiplying both numerator and denominator by that one. So that is modulus of it is root x minus root y into root x plus root y all divided by the same denominator, modulus of root x plus root y. So it is nothing but, it is a minus b into a plus b, a square minus b square. It is modulus of x minus y divided by root x plus root y. Okay, so that means modulus of g of x minus g of y, which is equals modulus of x minus y divided by root x plus root y. Okay. So but what about x? Here x and y fall in where? Closed interval 0 to 2. X and y fall in closed interval 0 to 2. So clearly it is root x and root y. X, root x and root y. That is closed interval, x fall in where? Closed interval 0 to. So it is less than or equals root x. Suppose root x less than or equals 1 and root y less than or equals 1, because it is in 0 2. If you choose this way, so it is less than or equals 1 by 2 into modulus of x minus 1. Okay, 1 by 2 into modulus of x minus 1. If modulus of x minus y less than 2 epsilon instead of delta, this is delta. If modulus of x minus y is 2 epsilon, then this becomes modulus of g of x minus g of y less than 1 by 2 into 2 epsilon equals epsilon. That is, if mod x minus y less than delta, then modulus of g of x minus g of y is strictly less than epsilon. That means this g is uniformly continuous. Uniformly continuous on where? On I. So this is our defined function g from I to 1 by g of x equals root x. Then here we prove that g is uniformly continuous on I. Now check whether this g satisfies Lipschitz condition. That's our requirement. Okay. Now we know that 0 fall in closed interval 0. 0 fall in closed interval 0. So g of x is root x. So what is g of 0? 0. Agreed? Okay. So what about the modulus of g of x minus g of 0? Modulus of g of x minus g of 0 equals modulus of root x minus 0 equals root x. Modulus of root x minus 0 equals root x. Okay. Or sorry, modulus of root x. So that means modulus of g of x minus g of 0 equals modulus of g of x. Root x means modulus, root x means g of x, modulus of g of x. That is, there exists no k greater than 0 such that g of x, modulus of g of x minus g of 0 is 0 itself. So modulus of g of x less than or equals k into mod g of x. You cannot be find out such a k there. You cannot be find out a k such that modulus of g of x less than or equals k into modulus of this one. Why? K into modulus of root x. Modulus of root x. G of x minus g of y equals root x. This means modulus of g of x equals root x. Modulus of root x. Okay. That means modulus of g of x minus g of 0 equals modulus of g of x, means we cannot be find out a k is positive such that g of x, modulus of g of x less than or equals k into mod x. Why? Because root x always less than or equals k into mod x. Why? Because k is a positive quantity. Since k is a positive quantity, then g of x or root mod x, modulus of root x always less than or equals k into mod x. So you cannot be find out modulus of g of x means g of x is root x, modulus of g of x means modulus of root x less than or equals k into mod x. You cannot be find out on such a function. Why? Cannot be find out such a function since k is positive. So k greater than 0. So there does not exist such a k which satisfies this condition. Means g does not satisfy Lipschitz condition. So a function which is uniformly continuous need not be implies it is a Lipschitz function. If a function is Lipschitz, it should be uniformly continuous. But a function is continuous on the if a function is Lipschitz, then it should be uniformly continuous on the given domain. But if a function is uniformly continuous on a given domain, it need not be implies satisfies the Lipschitz condition. Agree?